y'all, welcome to Miss Clark's chemistry class. I am still talking about acids and bases. This is my favorite video. You know me, I love math. If you've been waiting on a lesson about how to convert concentration to pH, pOH, this is the lesson that we're going to do that. So go grab your notes, get something to write with, a periodic table, and a calculator. Have you caught all of the lessons in this series? If not, it's because you haven't subscribed yet. Make sure and do that. All right, let's get started. Okay, so we're going to talk about how to calculate pH, pOH. I know you're like, what's pOH? We'll get to that. Concentration, this is molarity. We've talked about that in a previous lesson. So if you're not sure about molarity, go check that out first. Before we get started though, let's talk about how we can do these calculations and how we derived some of these formulas. If we're going to look at the self-ionization of water, because we're reacting water with itself. In a previous lesson, we talked about water being amphoteric. It can act as an acid or a base. Water will self-ionize. One of these waters dissociated. So if we were to break one of these waters apart into HOH, remember that's how water dissociates into its acid part and its base part. And then its acid part joins in with water. Then we're going to get this hydronium ion, H3O+. And then we're going to have this hydroxide left over. The main reason why I walk you through this is because I want to show you how one of the main formulas for acids and base calculations are derived. Now, if we go back to a previous unit in solutions and talk about the equilibrium constant, we know that the equilibrium constant for this reaction is 1.0 times 10 to the negative 14. And then if we talk about how to set up that equilibrium equation, remember that was reactants over products. And if you have no idea what I'm talking about, equilibrium constants, that's in a previous lesson. Go check that out. But to be honest with you, if you didn't check it out, just bear with me. It's really not that crucial that you understand that. I just wanted you to understand where this formula is coming from. Okay, so remember, the equilibrium equation was set up with products on top, reactants on bottom. You don't use gases, and you don't use liquid water. Well, dang, we've got liquid water here. So when we set up our products on top, we would have the concentration of that hydronium ion. Now remember, when we talk about the hydronium ion, that's the same thing as saying hydrogen ion because it's water plus one more hydrogen proton. Hydronium and the hydrogen ion can be used interchangeably. We're using the hydronium ion right here because that's what we really do get in the formula. And then we need the concentration of our hydroxide ion. Now I did not balance this, but it's already balanced. And I should have said that before we got started. I mentioned balancing because you know, if there was a mole ratio, then we would put those as powers right here, but there is none, so we don't need them. Let's get back to finishing this equation. Like I said a second ago, we don't use liquids and our reactants are both liquids. So there is going to be nothing on bottom. And then this is going to be one of the main formulas that we use when we're calculating the concentration of acids or the calculations of bases. Because if we know the concentration of the hydronium ion or the concentration of the hydrogen ion, we can figure out the concentration of the hydroxide and vice versa because of this statement. We know that when we multiply the concentration of the acid and the concentration of the base, then this is the constant that we are always going to get. So here's the same formula again. I went back to using the hydrogen ion because I feel like that's what we're used to seeing the most, but I wanted to comment on a few things before we go forward with math. If the concentration of the hydrogen ion is equal to the concentration of the hydroxide ion, that's a neutral solution. If the hydrogen ion is greater than the hydroxide ion, that's an acidic solution. And then if the hydroxide ion concentration is greater than the hydrogen ion concentration, then we're going to get a basic solution. So what is the value of the hydroxide ion and the hydrogen ion in a neutral solution? Well, we know that when we multiply those concentrations together, we get 1 times 10 to the negative 14. We also know that in a neutral solution, the concentration of the hydroxide ion and the concentration of the hydrogen ion, they have to be equal. We need the same number to represent the hydroxide ion concentration as the hydrogen ion concentration. So all we're going to do, divide this by 2. 14 divided by 2, that's just going to tell us that the concentration of hydroxide ion would be 1 times 10 to the negative 7. Cut 14 in half, that's 7. The concentration of the hydrogen ion would also be 7. If we were to multiply these two numbers together, then this is what we're going to get. A couple of things might have been piquing your curiosity, or you might have been thinking, is there a connection to this being a 14 and neutral, this being 7? I feel like a lot of times we come to this unit and you already have a little bit of information. For example, neutral solutions have a pH of 7. The pH scale is based on a scale between 1 and 14. That's not coincidental here. These numbers are what the pH scale is based on. So if we're talking about the pH scale, it's a scale between 1 and 14. Yes, this 14. It's the same 14. Where acids, now we've already talked about this in a previous lesson, but I'm just going to review it real quickly. So acids, they're going to have a pH between 1 and 7. Bases are going to have a pH between 7 and 14, leaving a neutral solution to be a pH of 7. We'll talk more about the pH scale as we continue on. If the concentration of hydrogen ion value is 1 times 10 to the negative fifth, is the solution acidic, basic, or neutral? Little shortcut here. We could do math for this problem, but if 1 times 10 to the negative 7 meant neutral, and we know that the pH of a neutral substance is 7. This 7 and this 7, they're the same 7. If we're talking about 5 right here, that's like saying pH of 5. Now, you can only use this shortcut. You can only use this shortcut when it's 1 times 10. 1 times 10. If we had like 2.1 times 10 to the something, you're going to have to use the formula and you're going to have to do the math. We haven't gotten to the formula yet. We'll keep going for that. But since this problem says 1 times 10, we can just use that exponent as the pH. pH of 5 is less than 7. This is an acid. Oh, there's those formulas I was talking about. I always give this cheat sheet. I never make you memorize these. If your teacher makes you memorize, they're really not that difficult to memorize. It looks like there's a lot here because they're written both ways, like A equals B or B equals A. They're written both ways. So it looks like there's more here than what there actually is. Let's see what all is here before I actually even read this problem. If you're given the concentration of hydrogen ions, then you could go one of two ways. We could solve for the concentration of hydroxide ions, and we would have to use that formula that we already talked about, that 1 times 10 to the negative 14 equals the concentration of the hydrogen ion times the concentration of the hydroxide ion. It's the same formula. I just have it written two different ways if you're trying to solve for the hydroxide ion or if you're trying to solve for the hydrogen ion. But it's this original formula that we've already talked about. If you're given hydrogen concentration, you could then figure out pH with this formula here. pH equals, here, let me write it. pH equals the negative logarithms. But you know what? We're not going to worry about logarithms because we're just going to let our calculator worry about the math. So let me go back to that. pH equals negative log of the concentration of the hydrogen ion. Now, I will say this about logarithms. Logarithms are based on powers of 10, and so the pH scale is based on powers of 10. So each time you change pH, you're not just changing the value by 1. If we're talking about the pH of 2 and the pH of 3, that's not just a difference of 1, it's a power of 10. So each time you climb or go down the pH scale, you are going up by powers of 10 or you're going down by powers of 10. Okay, that's really all I'm going to say about logarithms. You could go from pH to the concentration, and if so, we're going to use this formula here. The concentration of hydrogen ion equals 10 to the power of the negative pH. Now, you're like, what is that? Well, if you're looking at your calculator, the logarithm is the main function. The button that we're going to use here, this is going to be the second function of log. When we work a problem, I'll make sure and point that out to you again. Let's go back over here to hydroxide ion because we could go the same math problem. Here we went from concentration of hydrogen to pH. We could go to the hydroxide ion concentration to pOH. Now, pOH is a scale. It's also based on 1 through 14, but since we're talking about the opposite, OH instead of H, the scale is opposite. The pOH scale 1 through 7 is basic. Again, 7 is going to be neutral. That doesn't change. And then 7 through 14, this is going to be acidic. So the scale works the same way. It's a logarithm. It's based on powers of 10. But since it's OH, and OH tends to be, I like to think about OH as being opposite of H, then the whole scale is opposite. And so these formulas over here, to go between the concentration of OH to the pOH, it's the same math as we did over here. But the concentration of H goes with pH, and so the concentration of OH, you would use the pOH. So again, it's the same formulas. Let's write those so you can see them. It might be kind of small, and plus they're sideways. If we have the concentration and we're going to pOH, we're solving for pOH, then we would just use the negative log of the concentration of the hydroxide ion. And then vice versa, if we're going from the pOH to the concentration of OH, we're solving for that concentration, then we're going to use that power of 10 button, the second log, to the negative of pOH. You could never use the concentration of hydrogen to solve for the pOH. You would have to go around the square. That's why I like this visual for the formulas. Now, the last little thing that I've not talked about yet, if we're going from the pH to the pOH. Now, this is probably the most simple one. They're both based on 14, so basically you're just going to subtract them. The pOH is going to be 14 minus the pH. So let's just say that I had a pH of 2. The pOH would be 12. I got that because 14 minus 2 is 12. Or let's say the pOH is 4. What is the pH? Again, you're just going to subtract it from 14. So we're going to get 10. pOH, that means basic, and yet pH of 10, basic. Same thing. Now that we've talked about this formula sheet, let's actually work the problem that's listed at the top of this slide. The molarity of hydrochloric acid in solution is 3.2 times 10 to the negative 3 molar. Remember molar, that means concentration. And all these brackets we keep writing, that means concentration. It's all tied together. What is the pH? Let's talk about what we're given. We're given the concentration of HCl. HCl is an acid. That means it's going to have more H pluses. So this is what we're given. And we are solving for pH. So we are going to need to use, if we follow this arrow, that's where we're going. So this is the formula that we're going to use. pH equals the negative log of the concentration of hydrogen. pH equals the negative log of the concentration of hydrogen. This doesn't even really require much math. Your calculator is going to do all the work. So pH equals the negative log, the concentration of H, that's 3.2 times 10 to the negative 3. Now let's talk about how to put this in the calculator. I'm going to type it in as exactly in the order that it says. I've got my calculator in front of me, and so I am pushing the negative sign, not the minus, the negative. So negative log, I'm pushing that log button. You know what? Pause this video right now and go get your calculator so you can see how to push these buttons. Okay, I'll start over. Negative log, find your log button. It should be a main function. And then now we're typing in 3.2. Again, if you have been following my lessons, you know how to type in scientific notation, but it has been a while. Do not use the up caret in the times 10 and all that stuff. We are using the exponent key. Most exponent keys have an E, and it's the button above the 7. It has to be a second function. So look for the second function that says EE. Like I said, it's normally the button right above the 7. Okay, so do that with me. Second, the exponent key, the button right above the 7. And when you do that, here, this is what my calculator says so far. It says negative log, and then it put this in parentheses, and I put in 3.2, and then it's going to have that little capital E, negative 3, and then you don't really have to close the parentheses, equals. I am getting the pH, let me look back at sig figs, 2 sig figs, I'm getting the pH to be 2.5. Is this solution acidic, basic, or neutral? I sure hope you thought acid. It's an acidic solution. Okay, let's try another problem. 50 grams of HCl is dissolved in 2 liters of water. What is the pH? There is nothing on here that tells us anything about grams and liters. That's because I wanted to make sure you understood we're solving for the molarity. Remember, molarity is moles over liters. Oh dang, we don't even got moles. I gave you grams. That's because Mole conversions never go away in chemistry. It's the basic of everything chemistry is. Okay, let's do that right quick. We've got 50 grams of HCl. Let's convert that to moles. Grams has got to go on bottom, moles on top. I've got my periodic table here, and I see that the mass of hydrogen is 1.008. I'm going to add that to the mass of chlorine, 35.453, and we get 36.461. So now I've got to put that in my calculator. 50 divided by 36.461. And I am getting 1.37 moles. So now we can put that in our formula. We've got 1.37 moles, 2 liters. So the molarity of hydrochloric acid that we are using, the molarity, which is the concentration, put that in brackets, concentration is 0.69. Now we have the concentration of an acid, hydrogen, the hydrogen ions, and we are going to pH. I know it's the same problem, but it was 2 additional steps, 1 and 2. So I wanted to throw this problem in. So again, remember that formula is pH equals the negative log of the concentration of hydrogen ions. pH equals the negative log. And remember, we said that just now was 0.69. No powers of 10 to worry about here. I'm going to plug that into the calculator. I'm pressing negative log 0.69 equals, and oh, this pH is crazy low, 0.16. You can have decimals for pH. If the pH is 9.2, determine the OH. We are given the pH, but we want to know about the OH. Now there's 2 routes we could take. We could take route number 1, or we could take route number 2. And the reason why we've got to take such routes is because we're given pH, but we're asked about OH. Remember, pH goes with concentration of H, OH concentration goes with pOH. So we have to figure that out first. For this first time that we kind of have to maneuver around the square, I'm going to take you which way I think is the easiest. I think option number 2 is the easiest. I think going from pH to pOH to the concentration of OH is the easiest. That's just my opinion. So let's jot these formulas down, and then I'm going to give us some space to work. So remember, that was going from the pH to the pOH to the concentration of OH. So first, we've got to make this jump here. If the pH is 9.2, now remember, both the pH scale and the pOH scale based on 14. So we should only be able to go 14 minus 9.2 equals, and so that is giving us a pOH of 4.8. Now we're ready to go from pOH to the concentration of OH. And if we remember that formula, pOH equals the second log of the negative pOH. So 10 to the negative 4.8. Go back and look at your calculator. Find that log button. Look at the second function of that. The second function of log should say 10 to the x. And if it doesn't, look all on your buttons and find 10 to the x. So I'm pressing the second button, log, and it's giving me 10, and then the cursor's blinking right here. That's what it's giving me. So now I'm going to type in the negative sign, not the minus, the negative sign. 4.8 equals. And I am getting, I'm sorry y'all, I'm just noticing that I wrote pOH equals, and it was supposed to be the concentration of OH equals. Concentration of OH equals, and I am getting, with 2 sig figs, 1.6 times 10 to the negative 5. That unit would be M because it is molarity, concentration is in molarity. I hope you followed that. If not, let's try another one. If the pOH is 2.3, what is the concentration of H? Exact same problem, but the reverse. We are going to start here with pOH, and we're going to stop here with the concentration of hydrogen. Now again, if I were working this problem for my own personal benefit, I'm going to go this way. But I do want to make sure that we can go the other way as well. So that's not what we're going to do. We are going to go here first. We're going to go here second. So we're going to go from the pOH, we're going to go to the concentration of OH, then finally to the concentration of H. Just to kind of change it up, show us the other way around. The concentration of hydroxide is equal to the second log of the negative pOH. Okay, so let's work that problem first. So again, I'm going to do second log negative sign 2.3 equals. So I am getting the concentration of OH to be 0.0055. 0.050. Now we need step 2. We need to go from the concentration of OH to the concentration of hydrogen. Let me change color of pen so we can keep track with this. So that's going to take us back to that very original formula we talked about. 1.0 times 10 to the negative 14 equaling the concentration of hydrogen multiplying by the concentration of hydroxide. Now, if we were to look back at the formula sheet, I've already got that arranged for us. That's the formula it originally came from. So we have this. We're solving for that. So if we want to get OH to the other side, we would divide by the concentration of OH here. And so we've got hydrogen ion, the concentration of the hydrogen ion, 1 times 10 to the negative 14, divided by the concentration of OH, which is 0.0050. Let's put that in the calculator to find the concentration of hydrogen ions. So I'm doing 1.0, second, the exponent key, the button above the 7, negative 14, divided by 0.0050. And I am getting that to be 2.0 times 10 to the negative 12. Okay, so that showed us how to go around the opposite side of the square. And if you really need to see a visual of how I'm typing in this scientific notation into the calculator, I just linked a video up at the top corner. Go check that out. Were you thinking this math was going to be difficult? It's really not that difficult. It's really just about using your calculator and understanding how to use the buttons on the calculator. Not that big of a deal. All right, I've got one more lesson in this series. Make sure you stay tuned. Until next time, bye y'all.